the development of a workflow to study a compression mold and how we try to optimize it. So a presentation of the suspect here, it's compression mold in which is used to manufacture a plastic part that goes in between the two mold half. You have the bottom half, the top half. You put plastic powder in the bottom half, you compress it from the top, then you have heating cartridge, heating up the mold, and then maintaining a certain temperature to cure, to make sure the plastic will change, will enter in fusion, that the plastic will be hard enough and cured enough. It's a plastic cake, basically. So you have this heating cartridge providing heat. Once it's cured, you have these channels of water circulating inside the mold to cool everything down until you can open the mold and remove the part that was manufactured. So in the field, in the factory, the top mold cracked already, and the customer already designed these ribs to reinforce the top mold. But these molds are hundreds of thousands of dollars, and you don't want one of them to crack. So now they added the ribs. They are afraid that it's going to reproduce. So they want to study, they want to know if simulation can predict crack, fatigue crack of a mold. They also want to see if simulation can predict the curing time and if they can optimize the mold so that they can reduce the curing time and improve their productivity. So few challenges, few objectives here. We have to model the compaction, the heating and curing, and the cooling. We need to predict the curing time and the temperature distribution. Same for the cooling. We have to estimate the stresses out of the compaction and the thermomechanical stress. And we have to estimate the number of manufactured parts before a risk of fatigue failure. So how do we do that? It's a quick overview, but it includes a workflow with multiphysics. We start by simulating the heating process of the mold. The heating and curing, we actually include a subroutine to be able to change the amount of energy that we are getting inside the model to maintain a certain temperature. The CFD simulation, we have to model the water cooling in the jacket, in the channels, to study the velocity, but also extract the heat transfer coefficient for the convective exchange. Based from the last frame of the heating and the heat transfer coefficient from CFD, we can have the cooling simulation, which is the same as the heating. It's a transient heat transfer. Based on the temperature gradient at different increments from the heating and the cooling, we can have a structural simulation, which is a non-linear static with contact to study the thermomechanical stresses. And based on the history of the stresses, we have a duty cycle to proceed to a durability using FE-safe algorithm to predict the fatigue life of the mold. So it's a full workflow from A to Z involving multiphysics, and you can execute it all at once using a process. The next step would be to create a template of that process. So it's not only available for that exact mold design, but you can replicate that process with another mold design and spread it across the models that you have in the factory. But not only the process, now that we are able to run all at once, we can optimize the design. So we use something called visual scripting from CATIA. So again, it's highlight the power of having CATIA and SIMULIA in the same environment. Using this script that I'm really not familiar with, but it's on my training list for a few months, you can generate complex CAD geometry and generate a lot of design iteration in a very robust manner. So you will not create geometry that are unfeasible and would fail updating. And here you see that we played with the number of heating cartridge. Every big hole is a heating cartridge. And the small holes are the cooling jacket, the cooling channels. So we were able to change the number of each of them in different zones, different area of the mold, We play with the offset of each hole from the plastic part that was compressed and manufactured. And here, that video is from a tool called Design Space Checks. Design Space Checks is super powerful because after you've done your scripting or your parametric CAD, you kind of want to know beforehand if your design is robust enough and will be able to generate automatically without failing. So you don't run a process over a weekend time and on Monday you find out that most of the design failed. So you can run that tool up front before you proceed to the full design of experiment or optimization algorithm. So by playing with the number of cartridge, we were able to generate different design, same approach, a design of experiment, driving a physics simulation that is actually hiding different scenario, the heating and the cooling. And we've been able to generate, I think it was a dozen design and select the best one to proceed to a trade-off, selecting the best design ranked based on the objective, but also the design that was providing the best heating and the design that was providing the best cooling. And we were able to present that whole workflow to the customer. And if you have more questions, I can deep dive into that study because I can talk about it for hours. It's a lot of work has been done, but it's only feasible because everything is united in the platform.